Welcome to the fourth chapter of our Python for Geospatial Big Data and Data Science using the FASRC video workshop. In the three chapters before, we went over the structure of the FASRC, case study and some data sets that we want to work with and a research question that we want to answer here to showcase all the different options and things that we discuss, and how to then transfer our locally developed little toy example to the FASRC and really scale it to the entire data set. Now, let's address the question how much performance improvement that actually brings, because that's what we use it for, right? We want to use a high-performance cluster to obtain high performance. In the end of the last chapter, I asked you to time the runtime of your script. How long does it take to execute a script locally on your device, and how long does it take compared to the FASRC? If you haven't done that yet, I suggest to pause this video here and to really implement that. Just add these, I think it's 3 lines, and the exercise sheet for chapter 3 lays out how to do that. And run it and compare these two values. Locally, the same script, and then on the FASRC, also the same script. I'm curious what it is for you. In my case, and that's in my case, I used my laptop, which is a MacBook Pro with an M1 Pro processor. That's fairly new. I think that's now 2 years old almost. But still, it's 2 years ago. It was a fairly expensive machine, so that's probably still a little bit on the top here. But on average, I think we won't have too much of a deviation in what we see. In my case, it was like that. On my laptop, my script took 10 seconds, 11 seconds to execute here, and the same script on the FASRC took 18, like close to 19 seconds. Why is that? I was thinking that the FASRC is such a powerful network of computers, such a mighty system to use, and so valuable, especially if it's performance critical. Why is it slower? That can't be true. Well, it can. If we think back to what we discussed in chapter 1, where we were discussing the data structure, the structure of the entire network, how compute nodes and storage nodes are different from each other, and that the systems that execute a script are not the systems that have the storage or the data that we work with locally available, then this explains a lot what we see here. Because we see a difference, we would see a difference even if we had exactly the same performance, the same hardware. Now, in my case, I assume that the processor that I run my script on is also slightly, like the per core performance is probably slightly a bit better in a newer day laptop, right? If you run this on a just recently released chipset, then that will be per core quicker than a server which is not updated every single year. This is one thing. So the performance of each individual core might be a bit different, but the major part in this difference is most likely not about CPU architecture, but this is about the data needs to be loaded from a different side of the network on the cluster when you run this here compared to on your local device. Because on your local device, nowadays machines probably have some solid-state drive, SSD, hard drive storage systems that are chip-based, not physically anymore. There's not a physical disk spinning, but it's just a chip. And accessing data on these chips is very, very quickly. Like that's super fast. There's a lot of data throughput that we have here. Now compare this to our cluster where we stored our data with. These use physically spinning hard drives, at least at the time where this is recorded. And then also this data is not available right away on the machine that we process the data, but the data first has to be transported over the network to a different client, and this all takes time. This adds to latency, this reduces throughput, like in 1 second we just can't process as much megabytes as we can on a local system where everything is in the same place. And this explains a little bit why so far our script is most likely slower on the FASRC than it's locally. Why using the FASRC then in the first place? Well, we also discussed that in our first introduction chapter where we're discussing for which different kinds of applications we actually need something that we cannot possibly do on our laptops because the dataset is just too large, for example, and there's too much data coming in very quickly, so we can't process that. So there seems to be a way to leverage performance, just we can't use that. How is that, and how can we actually do that? Well, this is exactly what this chapter is about. Let's look a little bit into the computer science and the algorithmics behind making programs fast and how to optimize performance, especially for systems like this. I've showed you this slide before already. We were discussing a little bit the difference between a local system and a high-performance cluster system. Now, let's look a little bit about some different aspects that we haven't covered so far. Parallelization, for example. We have, as you might remember from the slides of the first chapter, systems with 48 cores per unit. And in our laptops, like, there is a pretty drastic increase in the number of cores available, but that's just far from what we have here. So the systems on a high-performance cluster system will provide, most likely in almost every modern use case, much more CPU cores than our local machines here. And so we have to program in a way that actually leverages that really makes use of multiple processing cores doing things at the same time. So we look at this concept a little bit. Memory is something that we can ask the FASRC for basically a random amount of memory, definitely much more than we can possibly buy for a laptop. I think if we buy a new computer nowadays, then you can possibly go up to, if you really look into some niche product, maybe get into 46 gigabytes of memory. The FASRC can easily do almost 4 times that. And you just request that. You just request, hey, Slurm, please give me a resource. I need this amount of memory. And a few seconds later, mostly, you get that. So this is something that we can use here, because in our programming we have to make trade-offs between what do we process and what do we keep in memory, what do we load, how often do we load something, what can we just store in memory. On our local machine, my laptop, I have 16 gigabytes of memory. That's not that much. I have a lot more here, but my program really needs to be able to use that. Storage, as we discussed that already, it's just a lot different on a local system compared to a network-based cluster computer, where I really have to think about that. So I can leverage that, and I need to think about that. Well, while this is not an obvious performance gain, the gain here is more, I have much more storage available for different use cases than on my local system I can possibly have. But therefore I need to think about, how is that built? How is that structured? How can I really make sure that I get the best performance out of that? The clue here is read every data only once, ideally, like every information that you have, and don't try to get the most important part of that, store that locally in memory, and then continue, read the next part, and not coming over to the same files over and over again and loading that over and over again, because that always requires that data needs to be transferred over the network, over the wire, and this is just slow. So make sure we have that in mind. Optimization, we can do a lot of code optimization, algorithmically as well. Just that is also something that makes a lot of sense for running programs locally, and maybe that's a good point to point towards. There is, of course, a trade-off how much optimization we put into, how much effort we put into this, right? Because if we spend weeks and weeks of engineering the best possible performance output, so it is really fast already on our local machines, then we probably don't need a cluster computer in the first place, but we also spend so much time there. So there is a trade-off between optimizing it to the last bit and using a very good state that is, that doesn't neglect the basic optimizations, but it's it could be faster. Probably all the programs you see or write yourself especially can be optimized in one or the other way. But sometimes it makes sense to think of if that makes sense, because the available cluster, although we shouldn't waste its resources, it's okay to just have a program running over the weekend. That's probably something you won't do on your local machine, your laptop, or at home, where it's probably annoying in the bedroom in the worst case. But it's okay if it just runs here and sits there for a few hours and just works on what it needs to do. And that might be just a better trade-off than optimizing something where it's a bit quicker, but you spend days and days in optimization. So that's also a balance that needs to be, that we need to strike. Code scalability, sure. Let's think of how can we scale what we do really to match these resources, these hardware specifications there. And make sure that we understand what is the system structure. There's always more that we can be done. Let me point back here. There's a trade-off to be made. Now here in this chapter, I want to show the most common ideas of how to do code optimization for such a system for you. And if that doesn't all stick with you and you don't feel like, I can easily apply that now after this half an hour of a video course here, that's fine. This is much more of a resource that you can refer back to once you get to the point where you feel like, I feel like he said something about this and that. Maybe I just revise the slides or the exercise sheet and see if I can get some ideas for, because programming is like speaking a language. You need to practice that, and you need to have an idea of what you can do in the first place so you are able to apply that in a later stage for your own project. Okay, good. Let's go into code optimization. What can we look for here? Well, we have I/O, that stands for input and output. That's what I meant with reading files really frequently and a lot, reading and writing, having a lot of access into the storage bits of our program. There's a lot more that we can go into, like caches and CPU level caches. There are different levels there. Then there's memory, then there's storage. Basically for you and here in this context, I would be happy if you just think about, where's my storage, how often do I access something, and this idea of ideally I only read it once, so I really minimize how often the hard drive, so to say, has to read this information from where it's stored and transport it to me. Memory as well. How can we make sure that we make use of the resources that we have? We don't have to be, we should always be memory efficient, but we have the luxury here to address a lot of memory in our cluster. And sometimes there are just no easier ways around that. So while we should keep in mind not to waste memories and really make sure of efficient memory use, it's okay if our program uses 30, 60, 100 gigabytes of memory, because that's what the cluster is built for. Parallelization is probably the most important aspect here. And that also goes hand in hand with test locally first, because iteration is just a bit easier. And especially when it comes to parallelization, debugging there can be very tricky. The library that I introduced to you, how to do parallelization here in Python, makes it fairly easy, and that's easy to replicate. It's just a few lines that you need to add and to transform your code to a parallelized version of that. But still, sometimes that can be tricky, and therefore just having quick access to everything and iterating, moving fast is a great benefit. So again, here that's just another hint to start locally and then scale it to the cluster. For example, my smartwatch even, right? This is a 3-year-old smartwatch, and still it has a multi-core processor on it. So I can, this is an architecture that is dominant over the entire industry. We always have multiple things that we can use to run code simultaneously that our code needs to adapt to. So if you have one thing that you can optimize, make it parallelization. You've probably, especially in a highly parallel environment like a high-performance cluster, the best chance to really get a speed gain for your use case here. Let's also look a little bit into code efficiency. I brought an example about dynamic programming. This example here computes the Fibonacci sequence. The Fibonacci sequence is a sequence of numbers that has applications in natural sciences, and basically, without having applications for it, it's just a sequence of numbers where one number is the sum of the two preceding numbers. So we start with 0 and 1, then we add them together. 0 and 1 is 1, so the next number is 1. Then the next number is the addition of 1 and 1, so 2. So we have 0, 1, 1, 2. Then the next number would be 3, because 2 and 1 would be 3. Then the next number would be 5, because 2 and 3 is 5, and so on. This problem, or the sequence, can be very elegantly implemented using recursion. So here in this function, we call a function called fib, and we just call it the same function 2 times. One time with the number that we are interested in, -1, plus the number that we are interested in, -2. The only addition to that is, if the number is less or equal than 1, then just return the number. And that is our anchor here, our recursion anchor, where we say like, okay, if the number is 1 or 0, then return 1 or 0, otherwise just return the sum of the two subsequent numbers here. While this works, and I believe that can be very easily understood, easily describable, basically it works in 4 lines of code, it is terribly inefficient. This kind of recursion, if I call this for the number 41, that's just a nice number that I've found out that my laptop can do in about half a minute, right? So if I call this function with the argument 41, then it goes here and says like, okay, I call the function itself with 40 plus 39. And the addition of these two numbers, then that will be the final result that I return. And then internally it iterates and iterates that over and over again until it reaches 0 and 1. Now, it takes my computer, as I said, half a minute to compute that. Let's introduce a very small little addition to this program, still recursion based, that makes it incredibly much faster. Here, in this version, we now introduce a little memory. This memory stores all the results that we have computed previously, because if you think of that, how you compute these numbers, you have to recalculate the same numbers over and over again. And we save so much time if we just memorize what we have computed before, and so we don't have to do that again, and only compute what we don't know until a given point. So here we have this little memory, and we just, whenever we call the function, we also give the function this little memory, and so it can add to the same set. This addition here, all in all, introduces one more line and makes the entire program incredibly much faster. So here for the same example, where we compute the Fibonacci sequence of 41, we now only have a few nanoseconds of computing, of runtime, that we need to compute this result. This is a remarkable difference. Now it gets better, because on the right-hand side, with our memory now, we have linear growth. So the more we add, the higher our numbers get that we want to compute, the more the load that we introduce with this program, that grows linearly, right? On the left-hand side, however, in our first version, we have exponential growth. And just to fathom what that means in this context, let's compute not only the Fibonacci sequence of 41, but the Fibonacci sequence of 120. Here in our example, this only takes a few nanoseconds more, almost the same, right? Very, very quickly, very efficiently, job done. In our first implementation, that's almost the same. It's just lacking this little memory addition here. This would take approximately the age of the entire universe. I cannot stress that enough. This little addition that we did to our algorithm to compute something changes the amount of computing time that we need drastically. And this is not done on any high-performance cluster. This is not done on any specialized hardware. This is on a very ordinary MacBook. That would run on your Linux, on your Windows laptop just as well. And I found this such a remarkable thing to intake. The little addition, the little change that we did to our algorithm of how we structure the program, of how we make use of computing resources, changes the execution time completely. And now, we won't always find such a magic little addition here to just speed up everything that we are doing tremendously, of course. This is an example that I chose specifically for this purpose because it demonstrates this idea very well. All I'm saying is there is a good chance that what you're doing, there are different ways to do that, and then it makes sense to investigate what takes how long and what are my options to optimize that a little bit and to shift it a little bit to really make sure that I get the most efficiency out of the system that I'm using. As I said, with a trade-off of how much engineering time I need to put into this to really make this run and make this work, of course. But all in all, just keep in mind there is a good way or a good chance that we find something to tweak it a little bit algorithmically. As I said, there is an application where we can do that in our program. In chapter 4, you will have a file called, I think, Global Sentiment Precipitation. .py, and this implements all these optimization ideas that we are discussing in this chapter. So please go ahead in the exercise. You will find some time and some hints of what to do and how to think of that and where to apply that. But if you're just curious, there is a ready-made implementation where we have all these ideas that I introduced to you now is already implemented, and you can just have a look and compare that with your own version maybe. Code efficiency parallelization, I mentioned it already, probably the most important concept to take away here, because the FASRC and all the other high-performance clusters are structured in the same way that we get more performance through making use of resources in parallel, and therefore our programs have to leverage that. Especially in the geospatial context, where we have a lot of data. For example, we want to plot a lot of points on a map with millions and billions of points. When we think of GPS traces that our phones compute, or social media posts scattered all over the world, this is just a lot of data that's happening there that needs to be addressed in an efficient way. This is one way how to do that. The idea of parallelization is probably, you probably have an idea of that. I just have a very simple example. Think of that. We want to sum all the numbers in an array. So now we can, in a sequential way, just ask the array or query the array for each value, go through that step by step, and just add and sum them up. In a parallelization implementation, we would just split the entire data set and then distribute chunks of this data set to different workers or different processes, and then the operating system will take care of that and distribute that to different CPU cores, to then in each worker and each core in parallel, like simultaneously, add all these numbers together, and then in the final step, when we merge all these results together, we can just add the results of worker 1, worker 2, worker 3, and so on together in a very simple and efficient way, because these are just a very few number of additions that are then needed to combine all these intermediate results. Like if we have this as a little Python example, it's very straightforward. You just generate a list of numbers and just sum them, really. And here is an example of how to do that in parallel with Python's onboard features for multiprocessing. At that point, maybe it makes sense to discuss or to say one sentence about multi-threading and multiprocessing, because you might have heard that there are threads as well as a way to parallelize something or do something simultaneously. In Python, what you really want to do in most cases is parallelization through processes, because there is something called the global interpreter lock for good reasons, but that makes sure that threads operate on the same in the same parent process, and therefore are not suitable for making use of different cores here, because the way Python works here doesn't allow you that. Long story short, use processes if you want to use multiple cores for your tasks. This code does exactly the same as the code above, just on multiple processes. So we split our array, our list here, in different parts, execute them in parallel on different in different processes, and then sum all these partial sums here together to get a total sum. Now, what you see here, parallelization isn't particularly easy and doesn't help to make the code nice, concise, and straightforward to read. So it will add a little bit of overhead, a little bit of complexity to your code, and therefore it makes sense to weigh where you want to apply that and at which part of the code you really want to use that, and where it's fine to run it sequentially, because there is not so much of a speed gain. So probably you won't run it for the entire code, for the entire script, but only selectively on a few different selected parts of your code. There's a lot more that can be said about parallelization in a computer science study program. There are weeks spent to understand this concept and to really get into the nitty-gritty details here. I just want to add here this little graph showing how much speed gain you get by using more and more cores. What we see here is an example that I ran on my laptop, where in our script, in our code, we have this one part where we take the tweets and want to augment these tweets with the precipitation data. So for each tweet, we have the coordinates from our mapping with our coordinate table, our join table there, and then we need to translate these coordinates from our counties to the closest matching coordinates of the grid from our precipitation data set, and then take the value of that day for that tweet, for that position on the globe, and augment these two tables with each other. This process can be done in parallel because every row is not dependent on another row. So it's really easy to apply that here because you can just split the entire data set and transfer a few of these lines to one worker and a few of the next lines to another worker and just do that in parallel. However, parallelization also will introduce some overhead for your program and for your processing. So you won't get just n times the speed if you use n CPU cores. And that's what we see here on the right-hand side. So if I use just only one core, then obviously I don't have any speed up. If I use a second core, then I have a speed up of 1.9, so almost double the speed. If I use a third core, I only have a speed up of 2.7, close to 2.7, right? So I have already lost a little bit of 10% per core of overhead, just because all these processes need to be administrated, they need to be orchestrated, is probably the better word, and the operating system and the code needs to make sure there's a lot to be done, right? The entire data set needs to be split. That's one task. Then it needs to be copied into the new processes that are spawned. That will take time. Then the processes do something, and then the result have to be copied back to the main process where the main program works to be then stitched together again. So all these things don't happen if we run something sequentially, but only if we do that in parallel. And then my system here has 8 cores on my laptop. And that's what we see here. We probably want a little bit of overhead of one core or a little bit of computing performance left for the system to orchestrate everything. Because here, if I really max out everything and use 8 processes simultaneously, then I don't have a single core left to do the administrative work to stitch all these things together. And what I see here is that I get a performance decrease. So I get the very best performance if I actually use 7 cores and 1 core is still left to maintain the rest of the program running, to maintain all the other things that are going on. In case of my laptop, there's, for example, a browser running, an email client running, maybe some background music. All that stuff needs to be handled somehow. And this is really why what we see here, that we don't have a performance gain if we max out everything that we have. But the gain that we have, the speed up, that decreases more and more the more cores we use. So there is a sweet spot depending on how big is the data set. You will have a better speed up if you have a larger chunk of data, so that the time that the processor is spending on actually running the task, you want to maximize that. Because if the ratio between the time that the processor is doing things to manage everything that needs to be done, like splitting and copying and retrieving and stitching back together, all that doesn't account for the actual result, right? That's necessary, it's necessary steps, but it's actually just overhead if we think of, we just are interested in the result really. And in that case, it makes sense to find a sweet spot between how many cores are we using, how often do we distribute that, because the more and more we do that, the more overhead is generated, and therefore the larger the data set that the processor really has the time to work on the task itself, the better the speed up that we gain through that. So this is because in our little toy example here, I don't have such a good speed up. However, if I apply that to the entire world data set that we have, and potentially even the entire decade of data that we have, then this speed up ratio will be much better, and I get a better yield of that. If you think, if you now feel like, yeah, I guess I get most of that, but maybe I want to have a little go on myself, you will, in the exercise sheet will guide you through how to do that yourself and how to play around with that. And please, I encourage you, make your own experiences, because that's ultimately how you learn programming, how you learn how to parallelize something. Try out, play around with the data. That's what this is for, and I hope you have a lot of fun with doing that. Just keep in mind, parallelization is definitely what you want to do. It's probably not a one-size-fits-all solution, and sometimes keeping a little bit of performance left for everything else that needs to be done here is probably a wise idea. Scaling on a high-performance cluster, I discussed that before already. differentiate a little bit between two types of scaling. One is vertical scaling, where we use more resources on the same node. So that's, for example, on your laptop, when you start using multiple cores. So far, you have used only one core until or including chapter 3 of this course, and now we discuss using really more cores that are available here. So that is vertical scaling, and then there's vertical scaling. And then there's horizontal scaling, where we grow the system by connecting multiple pieces of equipment, multiple hardware nodes. This is, for example, if we run our calculation script here for our analysis on one node for the year 2022, on another node for the year 2021, and so on another node. And then we have multiple nodes involved to really run this analysis for all these years one by one. That's definitely feasible if we split the data set like that in these two dimensions. One is across multiple resources on the same node, and then across multiple nodes. That's also something to keep in mind. We don't touch that too much here, but for example, if we do this for many years or for different years on different nodes, that's one example to do this with our data set here. Feel free to just start multiple Slurm S-batch jobs, and Slurm will take care of distributing that to systems, and most likely to different systems. Now for the exercise, screen your code for optimization potential. Use all the things that we discussed and really go through it line by line and think of that. First, start with measuring how long does which part take. Find the bottleneck, find out what goes quickly, what takes time. Give yourself the opportunity to learn a little bit how these things work, what is done quickly. Pandas, for example, does a lot of things surprisingly quickly, but loading these data sets, for example, takes very long. So how can we think of that? Then check, is there sometimes code that's run repeatedly? Can we save that? So that's a little bit the dynamic programming example that we discussed that took so long with the Fibonacci sequence. Are there pieces where we calculate something multiple times, although we actually could just memorize that? Hint, yes, we do. Exactly then, when we do this translation between our days and the longitude and latitude values from our counties, which are precise, to our grid addresses, where we query the precipitation data with indices that we calculate. Now we do this within one run for each county 365 times, because for every day we go through the entire data set and do that again. Now it makes sense to compute these indices only once for the first day, and for all these subsequent days, memorize or recall the indices in the array that we used for longitude and latitude, for example. So that makes a lot of sense. To save that here is exactly as we did in our example, and to make sure that we only compute things once really, and if we need it a second time, which we most likely will, then make sure we don't compute it again, but store it again, because memory is right now not our first issue, our first priority. Think about parallelization. Which parts could profit from parallel execution? There's, for example, loading the data set, right? That's more a bonus part here, where we say, like, okay, let's split the entire data set in different chunks and load that, because that just takes a lot of time. Or processing, augmenting the data set, our tweets with our precipitation data. That is something that is done line by line, so it can be easily distributed across different workers in the network. What improvement might have the biggest impact? Guess and try, implement that, and benchmark a little bit what brought how much. And as I said, we have a file ready-made for you that implements all these optimizations, and then you can benchmark against that, for example. Next, implement parallelization using Joblib yourself. For example, one example out of many possible, at the stage where in your code you really add the precipitation values to each of the sentiment values in your table. That is perfectly suitable for using parallelization, and you see also exactly this implemented in the code file example that we provide, but also the exercise script will guide you through this process and how to do this yourself. And then run the entire script using parallelization for probably the entire world data set, like the entire data set that you have already worked with so far. You can, for example, stay in 1 year, as that makes sense so far, or you extend the code to really make use of all the entire decade worth of data here. That's up to you. But this is what we think should be a good exercise to really get your hands dirty in how to implement parallelization yourself and get first-hand experience with that. If you want a little bit more, then we have 2 bonus exercise pages here for you. One is just continuing a little bit of this on this parallelization journey, and think about how you can use that for loading the data set. The fundamental idea is not to load the entire data set as we have used to so far, but only read a few lines of the entire data set in one worker and then the next few lines in another worker. This really can speed up this process and the pre-processing of the data set as well, and gives you a 2-digit number of performance, 2-digit % number of performance increase if you implement that. Also, for this case, we have a demo code in the GitHub repository, so if you're stuck, you can get some inspiration there. And lastly, of course, improve our analysis. The analysis that we've conducted so far is really rough. To make it a bit more statistically sound and a bit more robust, there are a few things that we could do and consider. For example, drop such days that only have very few tweets. As I showed you in the very first chapter, there are some counties where we have only 1 or 2 or 3 tweets for that day in that region. And for example, it makes perfect sense to just discard these places, or these days rather, just to have it a bit more comparable. So introducing a threshold to filter out all the days and counties that have too little or too few data here, that's perfectly reasonable. Likewise, the same that we can do for days where we have only very few rain days, because if we have this threshold of it should rain at least this and that amount, then that is entirely possible that there are some counties where we just have no or only very few days where there was more rain than what our threshold said. For example, I was working in the data of 2022 when I created this workshop, just for having an entire year worth of data. And 2022 was a particularly hot summer, so there were a lot of instances where we have, especially in deserted areas, counties where we have too little rainy days to really get into or add into this comparison. So here it also makes sense to introduce the threshold to have it just a bit better comparable with each other. Then we could also do add some statistical analyses. For example, introduce some effect sizes to really quantify how meaningful is the difference between the rainy days and the non-rainy days. We could also talk about statistical significance testing. When we do that, then of course it is absolutely important to just right after the next sentence then mention that we then would introduce multiple comparisons and running multiple statistical tests here, which would absolutely, in this case, drastically inflate our type 1 error rate, or the chance that we find some differences, although there are none. That's just how significance testing works when we have a threshold of an alpha level of 5% typically, and we then run multiple tests on the same data set. So here we really have to be cautious. We can, of course, employ techniques like alpha level correction in these instances, but I think how to manage that and how to do that, that's worth an extra workshop on its own. How to do the statistical data science here in this regard. For now, I want you to focus on how to work with the data, how to work with such a big data set, and also get a little bit into the habit of applying some statistical tests or some statistical methods or more dimensions like the effect sizes here to data sets and to data that you created like you did here in this example. Lastly, that's probably the most challenging here, but also arguably the most interesting. How about we compare only days where we have 3 days of no rain or 3 days of rain in a row? So not the first day, not the second day, but only the third day and the fourth and the fifth and so on, until there is a change. That would require some changes in our analysis routine, how we think of that. In the example that I have in the GitHub repository, I use loops to ensure that we have these 3 days of the same type really matched. That is potentially something that can be optimized and can be just made a bit more speedy and a bit quicker. If you have suggestions, let us know. It's actually a good challenge to think of how can you optimize such code and how you can get rid of loops there. But as a statistical analysis or more as interpreting the data, I think that's a very good idea to think of the analysis like that, of how can we compare like the same mode in a consecutive number of days. That's also something that is implemented in the demo code. I said it now, I think you believe me. If you want to have some inspiration here, have a look. The references, I said I said it now so often. You find it here. Global Precipitation Sentiment is the one file that implements all of these bonuses, all of these ideas that we discussed here in this last chapter, and I hope that is of help to you. Now, you find the exercise sheet as you used to here, scanning this QR code or just in the Git repository, and then everything that's left to say for this chapter is the summary. We have discussed optimization in our context of this little case study here. Optimization in general is complex. There are many things to consider, but I hope I could provide you the most important parts, what to think about if you design such an analysis and such a script to run on your own data set. Definitely, if there's one thing I want you to remember, then that should be parallelization, because I think that's a very valuable and powerful tool in your arsenal that you can use in such context, and definitely necessary. Like, you don't get around that really when you are thinking of leveraging the power of a high-performance cluster. Now, off-the-shelf solution, yeah, sure. It is dependent on what you're doing and exactly on your problem. So there is no one rule that I can hand you. I think it makes a lot of sense to scan your code for, is there redundancy and do you compute the same thing over and over again? That's always a good thing to think of. Make sure, how often do you really read a data set? Or is that something that you can potentially optimize and trade again a little bit against memory, for example, which you have here in this use case? And then, of course, parallelization, but we discussed that lengthy. I hope this was valuable to you and you learned something here. Let me know. And for that, we have one last little chapter in the full day workshop. It was an entire chapter. Here it's more a little appendix, how to reach us. Now, here in our last little chapter, in our little outro, I just want to mention a few things about this workshop again, and then, of course, point you towards options to give us some feedback, because that is super, super important to us. But first, the workshop. We promised that we would cover fundamentals in high-performance computing, especially here with the FASRC. I think we covered that. We discussed the structure, how it is built, what are the different components, how to access that in the web, in the command line. So I think that is covered. We covered some foundations of data science, probably not all of them, of course, but I hope enough to get you started. We were looking at 2 large data sets in different file formats, how to read them, how to process them, how to merge them together, what to consider when we do that, what is some potential pitfalls here, and what do we need, like our join table in the middle to combine these two. Some big data concepts using Python, mostly parallelization, but I think I said it now often enough. And some practical application, because we were actually looking at a very interesting, in my opinion, data set from social media, but also tightly connected to geospatial data, because all these tweets are coming with some geospatial locations that we can then use to interpret different sentiments and situations, how the people wrote about, how the people felt when they wrote about what they did there. I promised some learning objectives, that is learning how to analyze large data sets using Python in the FASRC. Yes, we did that in our case study here. Various tools and techniques of data science and big data computation. Of course, this is such a huge topic. We can only do so much in a one-day course or with these few videos here. But I hope I could get you started a little bit and interested in how to do that yourself. And I said it before, programming is definitely something that you want to use yourself and play around with yourself. So get your hands dirty and learn on the go. Prepare your work with your own data using the FASRC, or prepare you to work with your own data. I hope we did that with having a few different kinds of data sets and different angles of how we approach things. If you have any questions, let us know. This is probably the most important part. You can reach me, although I'm visiting here at Harvard only for a short time. You can reach me in my TU Berlin email, under my TU Berlin email address. And of course, Devika Jain and Xiaokong Fu, they are staff members here of the CGA and always happy to help you. Here are their addresses. You find them on the CGA team website as well. And our office is in 1737 Cambridge Street. Drop by. We are on the concourse level, just in the across the elevators. Let us know if there's anything that we can discuss together. We are happy to hear from you. I also want to point you briefly to other CGA projects that were carried out on the FASRC using big data techniques such as we discussed here in our course. That is definitely a page that's super valuable to check out and such a cool inspiration for myself. So I just highly recommend give it a click and have a look what my colleagues here at the CGA have done. There's some outstanding work, and I really want to highlight that here because it's timely, it's important, it's very modern research that is conducted here, and you are a little bit part of this now. Please give us some feedback for this course. Let us know what we can introduce the next time, what we can improve, what you felt was missing, what was good. Of course, let us know that. We as educators, as teachers, we absolutely live from your feedback. That is so important. Please let us know, because that is our way to learn from you, right? Let us know what you want to know the next time, what we should have a second and another workshop about. There are some discussions going on that we might have a second series about something connected to this and related. But please let us know how you liked it. There's a short Google form behind that link, and it takes only 3 minutes to fill it in. So that would be a huge favor to us. Thank you very much for your time. I think that's all. Let us know if you want to discuss something. We can't wait to hear your feedback and your thoughts and discuss your projects with you. And then everything that's left to say is thank you very much for the time we spent together here. And I hope you learned something. All the very best in your endeavors and with Python, Big Data, and the FASRC. Goodbye.